we present MIMIR, a multipurpose synthetic dataset for underwater navigation and inspection. In aerial and ground robotics, computer vision algorithms, such as localization and segmentation, have allowed robot autonomy. In underwater robotics, deep learning presents a promising alternative to follow the same path. However, most datasets used in literature are out of the water and lacking variation. Simulators then present a feasible alternative to fill this gap. Gathering underwater data is characterized by the high expense for robot deployment, the difficult accessibility of the environment, the limited availability of sensors, such as sonar or vision, and the difficulty or impossibility on gathering ground truth, due to the high cost of the motion capture systems, the absence of GPS, and the challenging imaging conditions. Existing real datasets for localization and segmentation are characterized for the limited availability of ground truth, which in the case of localization is usually inferred from an algorithm, or for the manual labeling required by segmentation. Therefore, this work proposes a simulated dataset for localization, segmentation, and depth estimation, recorded under 4 underwater scenarios, and furthermore, proposing metrics to assess and compare the variety of information comprised by the dataset in terms of image conditions and variety of motions. For gathering the data, we deploy a whole robotics simulation with the realistic renderings from Unreal Engine and the physics simulation from the AirSim plugin. The robot moves in the environment following a sequence of waypoints and a polynomial trajectory in between them. All this implemented as ROS packages. Then, for a given sensor setup, the data is recorded through the AirSim API while the robot is moving. The 4 underwater environments are as follows. All of them have pipelines for pipeline inspection, and we have 2 shallow underwater environments with more or less dynamic elements, such as moving algae, a deep underwater environment with different levels of darkness, and finally, we have an environment with a pipe covered in sand. The first metric introduced is the del entropy, which, given the image derivative in x and y, obtains the 2D histogram, which is used as input to the Shannon's entropy formulation, giving us an output value. This value is maximized for uniform distributions of the histogram and minimized for zero gradient images. High gradients indicate presence of non-distinctive features, which can be mismatched in SLAM, and low gradients could cause lack of features detected, which could lead to tracking failure. Ideal values for SLAM would be then intermediate values. As a comparison, we show that Yury has in general higher values for entropy, with its images providing many different intensity values. Aqualog has a more uniform range of intensity values that in general results in lower entropy. And for our dataset, we have many ranges of values, including very low values from very dark images. The motion diversity metric is obtained from concatenating the relative translations and rotations to then obtain their principal components from the singular value decomposition. From these components, we obtain a metric that gives higher values the more diverse the pattern of the motion is. Here, for our dataset, we have a high diversity in translations, but low in rotations. The SLAM experiments carried out allowed to identify the challenges for SLAM that the dataset presents, such as pure rotations, dark scenes, repetitive scenes, moving with respect to close-up objects, and presence of dynamic elements, all of these situations making SLAM either drift or fail. The segmentation experiments deployed state-of-art algorithms that showed the potential of MIMIR for training pipe segmentation models that can detect the presence of pipes within the dataset, but also in a real scenario. Similarly, MIMIR also proved its potential for training depth estimation networks, which showed promising results in a real pipeline dataset. In conclusion, MIMIR presents a multipurpose dataset for underwater computer vision, introducing metrics for assessing data variation in terms of imaging conditions and motion patterns, and presenting new challenges for SLAM, segmentation, and depth estimation. And finally, bridging the gap on availability of underwater datasets. Thank you.